Welcome to the Polymer Science Podcast. I am Dr. Alicia Buertes.
And I'm Jacob Scheckman.
In this podcast, we'll be speaking to researchers from around the world and talk to them about how their work is improving our daily lives. I hope you enjoy our conversation and that you learn something new.
Hello and welcome everyone to the Polymer Science Podcast. My name is Jacob Scheckman, and in this episode we'll be listening to my interview with Dr. Hyunwoo Yuk, an outstanding research scientist of mechanical and biomedical engineering at the Massachusetts Institute of Technology, or perhaps more commonly known as MIT. I reached out to Dr. Yuk after finding his work on the development of a particularly interesting surgical glue. Now, this glue can close and completely seal an open wound in seconds. Seconds! And the way they came up with this idea, it's absolutely barnacles. No, really, the whole project was actually inspired by sea barnacles. Mother Nature has always been a powerful inspiration for scientific progress. So, when Dr. Yuk and his team were tasked with designing a surgical glue that could surpass existing products, they recognized the robustly sticky nature of barnacles could provide valuable insight toward their cause. I mean, if you think about it, if you make a surgical glue, it has to be able to stick wet things together in a wet environment. And where can we find barnacles? On rocks, on wooden docks, even on whales and boats. They are everywhere in the ocean, and anywhere you find them, they are almost impossible to take off. So, how did Dr. Yuk and his team manage to mimic the strength and sticky robustness of these sea barnacles? Tune in now as we get this conversation started to learn about how they've accomplished this incredible task. Thank you so much to get back into it for agreeing to be on the show. I mean, I was ecstatic when you got back to me by the end of the same day.
Thank you. You know that researchers in university use emails almost like text messages.
Yeah, exactly. Well, and after I had come across the work that you had done, I figured your inbox must be pretty full these days. You seem pretty active. And also, congrats. As far as I understand, you've just defended as of December of last year, was it?
Yeah, I did. I actually wanted to defend far earlier than that, but I wish the COVID pandemic would end at some point. I can do an in-person defense, but somehow I just lost all my hope and just let's go for it for Zoom defense.
Yeah. Well, that's good. That's good that you were able to get it done. I'm sure your professors probably didn't mind having you around for a little more time as it seems to go. You have such an impressive CV and background. I was going through some of you have the website about yourself. Your work has been featured and highlighted on major news networks. Just to list, I see BBC is there, Fox News, Forbes magazine. It's pretty cool.
What I can tell you is that which I enjoyed, but also a little problematic that the big schools like MIT have a very well-working news offices. Mm-hmm. So they are very good at disseminating the work, and in some sense, it really helps the school to get attention. But I have a pretty bearing opinion about those media coverages because it's a great thing to have, and people can reach out for general public. But somehow it sometimes give a pretty, a little distorted messages, especially for starting grad students, etc. Sure. This media highlight is something that people have to chase off, but it's more or less strictly byproduct of anything that happened to a research outcome. But I have some kind of more complex opinion about all those things. But it's anyway good to see that general public can appreciate our research work because most of them would not likely subscribe research paper journals we see daily basis, but they should not have such a subscription, right?
It is surprising, and it's nice to have the general public become more involved in gathering this knowledge. So it is good to see. So to, I suppose, just kind of get into it. Actually, before that, I want to make sure that I'm pronouncing your name correctly. Is
Okay.
Hyunwoo Yuk? Is it?
Yeah, it's wow, you are amazing. You are the most accurate pronunciation of my name so far in the last 6 7 years. I think it's really amazing. Yeah, it's absolutely correct.
Well, that's good. I'm definitely going to leave that part of the recording in there just to brag about my correct pronunciation.
Yeah, like you know that like people pronounce it all the crazy way. Like, oh, that's a very similar.
Yeah. I might have a slight advantage. A TV show I've gotten into recently was actually Korean produced. So I hear some of
Ah.
the names. Maybe that gives me a leg up. Also, coincidentally, the protagonist in this show I'm watching, Sisyphus, is a genius mechanical engineer. So it makes me feel like I'm talking to the protagonist of that show now, as you, another genius mechanical engineer.
Well, yeah, well, thank you for good word. Although what I'm doing is a little quite far stretched out of mechanical engineering, but well, like now this boundary between fields are pretty blurred away, so
Hmm.
it's pretty common.
Good. Yeah, yeah. Well, let's talk about how you sort of got into the work that you're doing. As if you're telling our audience how you got into this field in the first place, a little bit about your educational background and what ultimately led you to focus on these biomedical applications.
Yeah, I think well, because I already kind of finished my PhD, and it has been like say 7 years to work on this particular field, and almost over 10 years to start the research when I was in bachelor back in Korea. So it's a kind of convergence or interaction between academic side of the life and the personal side of the life. If I go for personal side of the life first, that I like nature because my first dream was become an etymologist or scientist to studying insects. So the bio inspiration has always been there as a personal part of it. But what is really drive me to study this biomedical engineering or technology, which is I should say not very traditional part of the research area for mechanical engineer, which I did for bachelor, master, and PhD, all three mechanical engineering, but it's not really common. Is I had one little brother was around 10 years younger than me, and when I about to go out to US for my grad studies, he got really injured heavily, like a traumatic injury. I had to spend like almost 2 years with him throughout the hospitalization processes, starting from the emergency care, ICU, and general hospital, rehabilitation hospital, etc. So I had a pretty good amount of consumer experience on medical product in variety of different types and surgical applications of variety of different types. And I am actually was not very happy with all those things because many of them didn't work very well, which immediately translated into a patient, which is my brother's, a pain or like a unfavorable health, like a healing processes. So that part is always kind of going through throughout the whole study, but it was only recent 2 to 3 years that I actually wanted to do something because as an engineer or scientist in general, interest on something and having a right knowledge or capability to do something meaningful is quite different thing. So I think that really resonate with my academic side of the journey, that it was around the 2 to 3 years ago that I feel myself ready to tackle on those problems, because when I first get to the grad school, I did robotics in my bachelor's degree, but all the robotics research labs in MIT Mechanical Engineering Department didn't want to hire me. So I had no place to go for robotics fields. So what I had to choose is something else that related to my background about bio-inspired robots, but somehow not robotics because no robotics lab wanted to take me. So what I ended up is soft material lab, my PhD advisor who wanted to build a 3D printer to make something made out of a soft material, but the 3D printer is a machine. It's a robotic system. So he sees some interaction between what he wanted to do and what I can do, the building the 3D printing system to print some soft materials. So I joined the lab that I got a PhD degree and worked a while, but turns out that printing is not really easy topic to do a good job. So later I just more or less accidentally start to work on addition of a hydrogel, but nothing to do with the biomedical, but more or less like a material and mechanical side of it, just to make a very robust addition of a wet material like hydrogels and all those kind of things. So for first 3 to 4 years of my grad study, my expertise become sticking something very robustly on a wet surface. So that was something what I actually got on my master, and I just doing very well on it. And there was an event that in one day, my PhD supervisor and I got an email from a totally new person we never met before in MGH in Boston, a big hospital. That clinician just sent the email to us that say he is interested in biomaterials in general, and he wants to talk with us to see potential collaboration. And it was the first time I had a chance to ever communicate with a clinical person. So it was a surprise, and we met him, and he was a very nice guy. And we immediately kind of very feel good about each other. And so we kind of share a lot of things we do. And then I felt like, oh, maybe this guy is the person that I can ask something about my interest about a biomedical thing in general from my personal experience and what I can do, but because I have no idea about clinical things. So I showed I don't know what's going on, but what I can do is the sticking wet material very strongly. And that's what I write on many papers so far. And he sees that, and he just tell me immediately that, well, you have to study tissue adhesive, which is very commonly used in operating room, but he and his colleagues are really not happy with the existing ones. So that was 3 years ago. And since then, I think we form a very good team, and somehow I felt very nice because my personal side of the life and interest and my academic side of the life, which I didn't really expect it, but somehow happened to I studied as a sticky materials. It kind of feels like a converged accidentally. Since then, it has been 3 years we work on this tissue adhesive and silicone applications, and we published quite many papers on a variety of different form factors, variety of different mechanisms. And that's just one of the most recent work it just published, those barnacle thing that was also interesting thing. But basically, it's how we ended up doing this medical sealant businesses while we actually didn't start from all those background, myself or our research team in general.
Incredible. What an interesting journey. So all leading up toward tissue adhesion. So I'm a little bit curious how, since the medical researcher came along sort of out of nowhere, how is your research approach affected by now having clinical medicinal aspects?
Yeah, I think that's it's a really good question, because I think the impact that I actually start to work with a clinical expert was very pivotal, not just on my area of research, but the general approach and research. Because actually, I did well in my earlier research period in grad school. I published a bunch of papers, but I always kind of felt like a little unsatisfactory, particularly because I think myself as an engineer. But the issue is that when I did some work, it's very common in many fields, including myself and other people, that it's almost like a research paper we write doesn't have a customer, doesn't have a target. Well, we just sell something for ourselves, like only for academic community. And we really don't know what's going on after that's been done. And we just switch to another topic, write another paper, and it's very trend focused whatsoever. So I did a lot of work, but I actually have always having an underlying feeling that this is just a paper, literally paper and nothing more. And I had to keep changing my topics on different areas because I cannot write a so-called good papers if I try something first and then I have to chase for another novelty, another novelty, another novelty. So novelty-driven research is really kind of make me a little fatigued. And then this clinician comes in and I start to have a kind of reckoning that, first of all, it's very interesting to me because it have overlap with my personal life. But I start to kind of talking about problems that have a real problem that I can talk with the doctors that had a problem that actually they suffer when they treat with patients. So the failure or absence of a certain solution on a certain problem is actually causing people to suffer and die. And then I start to feel like, wow, this process suddenly feels realistic that, I'm doing something that is really, the actual problem is out there instead of a problem that I imaginatorily made myself to claim novelty on a paper. So it's a process that I really experienced and enjoyed throughout the last couple of years with the clinic expert that is really feels like I'm really doing engineering, that the science of solving problems. And I clearly see what is the problem and what's the consequence of the problem and what will be the benefit by having that problem being solved. So I suddenly feel like although the research topic and the methodologies and all those things are not very big different, I just keep doing the research I did and keep doing well. But just more attitude-wise, it feels like I now start connected with the real world. And my work is to start to influence little bit by bit to the actual world instead of just circulating within the academic realms, then making a paper. But it's more like I become more like an inventor rather than just a scientist. So it was very cool feeling. And I think this is something be very interesting to experience or having some attitude towards such a mode for most of the engineering discipline people, especially even during the grad study, because that's something that I really felt very frustrating in early years in my grad study. That I'm an engineer, but I'm really not solving real problem. Then now that I feel like a problem becomes far more complex and challenging and sophisticated than I did like 5 years ago. But it just feels more rewarding in a sense that I can feel the connection with the real world myself when I'm doing something.
Yeah, absolutely. I commend you for in the very beginning, having to get through the rounds of just chasing novelties and sort of trying to get through the question of what am I doing this for? And I'm happy that you found the answer. You found this, like you said, the reckoning that made this as rewarding as really any researcher dreams that it could be, right? I feel, as again, another graduate researcher myself, coming into a program, I wanted to be able to do something where I felt like eventually this might make an impact. And so that's great to get that feeling at some point, right?
Yeah, so that's true. But what I really kind of think is important for me throughout this process is that there are a lot of important problems out there. And many people say something is important, but I think the best problem to solve for engineer is the personal problem in some sense, because it's very difficult to resonate with somebody else's definition of important problem.
Yeah, that's very sound advice. Now, when it comes to the applicability and really getting into the research that is addressing relatable problems, it seemed like, I think it was last year or 2019, you published first on the double-sided sticky tissue tape. Can you talk a little bit about that project and whether or not this eventually sort of led to the new barnacle-inspired glue?
Yeah, so that was the first paper that our collaborative team worked on, this biodisc or tissue disc direction. And I think that work itself is not the all things we do, because as you can see from our set of papers, including the most recent one, this barnacle things, we just kind of keep doing more work to solve the more problems, because first solution cannot be the perfect solution from the beginning. But I think that work was very important for me because that work is the first work in my whole research career that I actually saw and did animal study and any bio-related thing that first time, which I have never had a chance to actually get nearby as a mechanical engineer throughout the whole educational process. So it was very kind of a beginning of my exposure, which now I'm very familiar. So I just do those things daily basis. And second thing is that I think that particular paper is really, I think it can be a good example for other researchers that how the people who were not in biomedical engineering can bring a little bit new perspective to the field in a way that a little differ in approach in solving problem. For example, there are a lot of biomedical engineers and tissue engineers and biomaterial people with a strong focus on biology and tissue engineering, cell culture, all those things. But it's a little different in our world of mechanics of the material is that we live by mechanism. Like we always chase, discover, and formalize a more fundamental language of why something is working and how to make something. Instead of finding out a specific combination of a material that just work in particular situation. So in that first paper, which we tried to keep repeat the approaches and again, is that instead of focusing on a particular combination of materials and their form factors that do the good addition, which is the purpose, instead of just focusing on that, we going back a little more fundamental way that what makes the existing solutions cannot make stickiness or adhesion to the wet surface in fast time, I say seconds of time period. Nobody could do that. And we had to understand why question first by using our understanding of the mechanics and physics and all those things. So although that part is quite much hidden in that paper because we had to show this impressive ability of forming adhesion to the wet surface and its application as tissue sealant, etc., as a front page of the work, because that's something that our peers in that community understand better. But in that paper, we discovered a mechanism that some of the animals are actually already using that how to form adhesion in second time scale on the wet surface. And we found that mechanism and we formalized that. We developed a mechanical theory models to explain why it is so. And after all this being done in our backup door level things, and then it's the beginning of the time for me to find out and try and mix variety of different composition of commonly used hydrogels to implement that mechanism into the biomaterial and then test a variety of different things for performances and toxicity, biosafety, etc. So that's something that we are very proud of because that's not material specific or application specific knowledge, but people can actually use for a variety of different purposes by changing or choosing their own choice of a nicely loved material. But so we are trying to repeat the same thing in this recent paper, like barnacle thing, that people may only see the barnacle-inspired glue that seal the bleeding wound as the front page, because that's the most important outcome of the work. But what we are actually proud of as a mechanical engineer is the behind the mechanism that we learn from the barnacles glue, that how they can actually form adhesion on a contaminated and wet surface. And we actually bring those mechanisms and learn it and translate that into the language of the mechanics. And we a little do some calculation and extracting out the conditions that have to be satisfied and find out the material that satisfy that conditions and then test all the things and do the animal study, etc. But sadly, again, that one is all in supplementary material because the peers in this community doesn't understand or doesn't it doesn't take it as the main piece, but they more like to see material.
Yeah, what's the material? Does it work?
Yeah, how it works and how great it works compared to the existing solutions or product, etc. So I think it's a kind of all those papers we publish have some hidden thing, hidden jewel that we like as a mechanical engineer or mechanics of a soft material people, but they are quite much in supplementary material, which virtually nobody really reads much.
Right.
While the outcome of that understanding that we translate it into an actual real world object, such as material and its performance, is bring up into the front page together with some by inspiration declaration, which help people to understand better. So that's how it goes, and it's a kind of but what I want to say is that although they are hidden in supplementary material, but I believe although in short term like now or in coming years, may still people only see those front face meta, such as a barnacle-inspired something is so cool, something like that. But we have some confidence or belief that those more fundamental side of the picture of all those tough problems and what kind of mechanism we can propose to deal with those tough problems more fundamental level with some theoretical understandings behind it may have a more impact or help to people over time. Although this medical device itself looks like more cool now, but as an academic perspective, those may be useful in the future because people may learn from that mechanism and they may choose a completely different composition of material or approach, and they may use a completely different application where the same challenges just to come, but in different application. So those are something that we really like as an academic person. But now, because we are trying to commercialize this thing throughout the translational process, like I have to bring my another personality that those things doesn't matter. What is matter is patent application and this particular product, and I have to bring this into the market. I have to bring this into the GMP manufactured product. I have to bring this through the regulatory process. I have to make some convincing argument for the investor to bring like a couple $1 million to do whatever. So that's just my feeling. Like papers have a different things that actually in impact. So those papers give me a kind of very duality of the feeling, like what I really like as an academic person hidden in a supplementary material.
Of course, it's always the hidden part. I like the way you describe that, having to sort of put on different hats, be a different person, one for the marketing, saying, look at how good this product could be, and then the academic side. I think it's incredible the way you describe too. As exciting as the end product might be, you've also uncovered this amazing mechanism in how the barnacle can so strongly adhere to all these different surfaces. And actually, I want to talk a little bit more about the journey you went through in the barnacle-inspired product. And I'm just going to read a couple of titles here. The title of the article you published was the Rapid and Coagulation Independent Hemostatic Sealing by a Paste Inspired by Barnacle Glue. And for our listeners that may want to learn more about this without having to read the intense journal literature, there's an article published on Wired Magazine written by Max Levy called "This Barnacle-Inspired Glue Seals Bleeding Organs in Seconds," which really gives people an idea of what this could be for. Now, how does this journey start for someone, right? I imagine, you don't think, you see barnacles and think, I'm going to scrape some off and grind some up and see what's inside, right? What's going on from the inception of this idea to really bringing the idea out onto the benchtop in lab?
Well, I think that one I really want to share to as many as people possible, because what I actually really experienced in this particular project in terms of bio-inspiration or nature inspiration is really typical process, how and why bio-inspiration or nature inspiration has been so powerful approach in so many different fields. Here's the thing. Absolutely, I never thought about a barnacle to just see that it's going to be helping, but there is a kind of common thought process how people get to a certain creature or animal to solve the problem. So here goes this like that. There is a problem, mostly a very complex and sophisticated and daunting problem that human brain's rational thought alone is very difficult to bring up the solution. So there's such a problem a lot. And bleeding tissue is just basically a one of the such a thing. So once have that such a problem, and then what we do as an engineer is converting that situation, the problematic situation, into engineering or scientific language that we can more specify. So in my case, for this particular project, so the bleeding and how to seal it is more engineering or scientific language is this. To do that, to seal such a bleeding wound, we have to form an adhesion to wet as well as contaminated surface, because blood is contaminant. So then that's the definition or scientific definition of any problem. People can do that. And the problem is challenging enough that our rational mind cannot come up with a simple scientific or engineering solution. Then what we do is there is a general principle of relying on evolutionary solution optimization process that all the animals do, because animals do not live everywhere. They live in their habitat and they thrive in habitat. And habitats have or environment they live in or are doing well have a specific characteristics. And the animals that live very well in that or thrive in specific habitat with a certain condition is doing so because they are being evolved to doing great in that particular condition. So if we can find out a certain environment or condition that exists in nature that shares the condition that we are trying to tackle as the problem, and that's the first step. We find out an analogy between the problem that we want to solve and the natural habitat or environment that shares the same problem. And then next thing is we take a look at the animal that's doing so well in that particular environment, especially in survival way. And then they should have something to fight with that particular harsh environment or condition. And therefore they survive over time. And then we find out that particular animal, they do have something, they should have something, and then take a look ourselves or searching some academic literature that studied that particular animal, that what they exactly they do to do well in that particular environment, and they do have something. And then that's the solution they found throughout the evolutionary process, and we learn it, and then we have to reverse engineer or more like get inspired from that solution to extract out a solution that we can actually use ourselves in engineering scientific way for our original problem. So in my case, if I make example, I translated a problem of how to seal the bleeding tissue, bleeding wound, into an adhesion to the wet and contaminated surface. So because it is a wet adhesion, we always take a look at the seas or rivers and all those wetty places, watery places. And I see a lot of creatures in Google photos and images, etc. And I tried to find out that creature that particularly is sticking on a dirty surface. And the barnacle really catch my eye at that moment because I could find the photos of super dirty rock populated by barnacles. I could find the super rusty metallic surfaces that populated with the barnacles, and I even could find animal like fishes and whales covered with a barnacle. So basically, I could see that this creature, the barnacle, can adhere anywhere. Doesn't matter how dirty it is. So I just got fixed on that barnacle, and I had to study more papers about a barnacle. And thankfully, some biologists studied the barnacle because they intrigued in the same way. And they actually did a very, very detailed confocal interfacial analysis and chemical composition, all those things that they actually studied what this barnacle actually secrete to stick on those dirty surfaces. Then they even studied the stepwise process of what they do. And then I find out that, the secret of this barnacle is they having a two component in their glue. One is a sticky protein, which is not surprising because they stick well. But it's a little interesting part is they have oil together. So those sticky proteins are suspended in oil. So they have oil and the protein together. It was a little counterintuitive composition. So what those biologists find out is that these barnacles actually secrete the oily component mixed together, and the oily components are actively pushing out all those contaminated material from the surface, and then those clean surface can interact with the DC protein to allow them to stick tightly on whatever dirty surfaces. And we just got say like eureka kind of thing by learning that and take out exactly the same mechanism and do some calculation that, wow, it's really true. And then pick up the other material that commonly used in the medical device realm to serve the different functions of oily substances and sticky substances, pick it up. And
just real quick to make sure that I understand, the barnacle is sticky. It's secreting in oil to get rid of the contaminated area, or clean the contaminated area, and then the proteins are the actually sticky part.
Yes. So
okay.
Instead of having only sticky part alone, they actually have a cleaning mechanism together based on oily, like hydrophobic substances. So that was a very counterintuitive because the glue that contains like a non-sticky component together, and that was a secret for barnacle, and we just inspired it because the situation is exactly the same thing. Maybe for barnacles, though something they have to clean is maybe some algae or like whatever dirty thing that happened in the water environment. But for us, it's just blood.
In the MIT news article, it was written that the part of your paste has to include a blood-repelling component. And so you're saying the blood for us, when we're trying to patch up an organ or skin, blood is the stuff that gets in the way of the adhesive stuff.
Yes.
Yeah.
Yeah, and it's a horrible fluid. The blood is a horrible fluid, not just because it is bad, but because it is not a simple fluid. The blood composition is water only takes 50% of the volume.
Water is 50% of the volume of blood, and that's it.
Yeah, and the remaining 50% is consisting of cells and protein.
Wow.
So blood is actually a very, very, very dense, solid material, but it just looks like a viscous liquid because those cells are very squishy cells, like the red blood cells or white blood cells. But it's actually only 50% water content. The remaining half of the blood is cells and proteins. So that's why they are so perfect contaminant for almost every adhesive.
Gotcha. And so it seemed like the solution to that problem, to sort of cleaning the area, repelling blood, was you used a silicon oil in your paste.
Yeah, we actually used the multiple types of oil, but we just choose a silicon oil because it's like the most well-defined fluid we could find. And medical grade silicon oil have been already used as lubricants for a variety of implantable devices in the clinical realm. So we just pick it as a model material. But there are we also tried many other oils like more like a fatty acid, etc. But as a research article that establishing the basic proof of concept, we always prefer something super well defined. So we prefer the synthetic material that we really know about it.
Right. And that's what you were touched on earlier, right? You were also trying to develop this fundamental process so it's easier to do so with well-defined properties. Yes. Right.
Yes, because we know the physical property is super well-defined and doesn't vary much. It's very reproducible. So it's kind of great.
Yeah. The whole thing seems kind of great. So you approach the problem of, I need a material that can, in a wet, bloody environment, close a wound. What are the general properties that are needed for something like this? So say whether you were developing the double-sided tape or you come to analyze the material physical properties of the paste once it becomes a cross-linked network, what kind of physical properties are best for approaching this problem?
Yeah, so I think the reason we actually did interesting work in this particular setup problem is because the requirement that you mentioned is very mechanical from the beginning. It just once it stick to the surface where we want to seal, and then those material have to be robust and strong and soft, and all those something that that it have to be soft to match the mechanical property of the underlying tissue. Otherwise, the tissues, our bodies try to reject it. So it have to be mechanically soft, yet it has to be robust. So therefore, it doesn't like break up or rupture easily.
Mm-hmm. Mm-hmm.
So it's basically have to be something like a little gummy material that are sticky and not very easily peel, like break apart. And so that's a very mechanical side of the properties or mechanical properties. So that was easier for us to understand and optimize. And the other side of the very, 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 very important property is for this type of medical devices, especially implantable medical devices, that it should be okay to use inside the body.
Right.
It should be biocompatible. It should be biosafe. And the material that we made which is fall into this category, is you have to be bioresorbable or biodegradable, because the people may use a sealant to help their surgery or bleeding and all those things, but nobody wants to do surgery again to remove it. So it really have to go away over time once it is used, as the injured tissues are being healed. And once the healing process is completed, they just have to go away gradually. So eventually remaining nothing but just the scar tissues that be there, instead of people have to open the space again and pick out those undegraded pieces. So that's a very bad idea. So basically mechanical property to serve as a sealant, something similar to whatever we use from 3M for like a leaky pipe, etc. But because it is being used inside a living organism, it have to be biocompatible. It should not cause a crazy tissue response that make a lot of bad things, and eventually have to go away throughout a certain period of time, not to do a readmission surgery, to just the removal of those implants.
Mm-hmm. Now, in the recent Nature publication, there's a section that reads that the paste exhibits gradual biodegradation via resorption by macrophages. So I imagine this is sort of what we're talking about now. This is the process by which it seems to be breaking down, whether it's the body's doing it or it's doing it on its own. Can you talk about what's happening there and maybe break down that statement?
Yeah, so there are basic chemically two ways of materials are going away. And there is a variety of different ways of being cleaned out of the body. So if we focus on our materials here, as chemically, it should break down like a smaller pieces of material or fragmentization or polymer chains by either hydrolysis, because it is a lot of water is out there, or enzymolysis, because there are a lot of enzymes that digest a variety of different materials. And once that thing happen, the whole chunk of material becomes smaller pieces. It's like become broken down into smaller pieces. And then the small fragments is further being digested by cellular entities such as macrophages, basically a cleaner of the body. And they break down things even smaller. So when they are small enough and there are still residue, and they start to be cleaned up by lymphatic systems and go through all those things in our body, and eventually ended up in either digestive system or urinary system to get out of our body as a form of the urine or feces, etc. So that's basically small fragmentization, either by hydrolysis, just water-based, or enzymolysis, enzyme-based, and also being helped by the digestive cells out there. And once they become small enough to go through this cleaning system of our body, eventually get out of our body through urine or feces, and then we are free of those material at a certain time point.
Mm-hmm. And so during that process, is there any risk of, or say while the glue is being applied to a wound, an internal wound, is there any risk of small pieces of network or even network precursor molecules that might get into the bloodstream?
Yeah, that's a really, really good question. And that's a so-called microembolization or embolization. So it's some small fragments, either by material itself or a kind of small blood clot that being induced by the material is get into the bloodstream, and it somehow clogs somewhere middle part, and it causes lots of problem. And I think this embolization or microembolization is nowadays particularly popular, or not popular, it's very well known, because some of the COVID vaccine is actually their like side effect is those embolization.
Oh, interesting.
So the people have a problem, after getting some vaccines is, especially some vector-based vaccines such as AstraZeneca and those things, although it's very rare, but they do have a side product of embolization because some interactions the vaccine and human body can generate some small blood clots. So that's a very, very, very dreaded outcome. In hemostatic agent or like this, like a sealing product, even in medical FDA approved product, we like as a research team, it's something that we have to do over time. But there are products that already undergo all those developmental processes. So there is always something that called the contraindication, that the situation and or condition or disease that a certain product should never be used because of the safety concerns. So so that includes a lot of things like don't put this into large open vascular wound so that it can actually easy to go into the bloodstream and cause all those problems. And it's the same for our case as well. But for those product that is already out in market, they actually undergo a lot of processes themselves over quite many times. So they already find out the contraindication to be declared or recommended by FDA. If in our case, we do have some understanding, but that's something that we have to do with some investment and due diligence in over some more developmental period while we are pushing through a regulatory process. Then we have a better idea that these are the clinical situation that this should not be used in patient because it have a lot of a risk, particularly those embolization risks, something like that.
Right. That's very interesting. I'm glad you say that. I was very curious if there were any kind of pre-existing conditions in which a product like this would be not viable. So that answers that question. Thank you.
Yeah, so it's a medical device, drugs, and all those clinical things that actually have to be used in human have a very narrow indication and also strict contraindication. That's the condition of getting approved for human use. So I think basically why the drugs and all those medical devices take so much time and so much money to get FDA approval. It's not used to buy a good food for FDA officials. It's not like that. It's just because people have to do a lot of tests and a lot of search process to really boil down the condition that it can really safely be used for human without worrying crazy things happen, even though there are rare things, but statistically unlikely. So it's really figuring out those conditions it can safely be used and it should not be used. It's kind of defining these things over the year of time period is all should based on science, right? People cannot say I think this is gonna be dangerous, so therefore it should be contraindicated. I feel good about this application, so let's indicate it. It's not working like it all have to be based on solid science-based data-driven decision and generating those data in human scale or for human or human scale large animal takes money. So that's why it's so taking a long time. It's taking sometimes tens of hundreds of $1 million for each product or each drug. It's just because people have to spend the time and money and a lot of people in collaborative manner to develop those huge database from which people can make an informed decision about where it can be used and cannot be used.
Let's say, it's 10 years from now and it's finally, you've just gotten the FDA approval for this. Where would you envision this can be used, right? Is it say, anywhere from being, taking a gunshot wound on a battlefield, or can I, say I'm on a hike by myself in the woods and I fall and I cut my leg? Can I use it for putting on my leg instead of a big bandage? Right? Is it that huge range? Where would you envision this could be applied?
Well, that's something that I really personally learned a lot in recent period, especially when I tried to do some translation stuff. As a researcher, if we just do dream wildly, we just wish this can be used in anywhere people can get help on sealing whatever bleeding wound of any kinds. So that's my hope. But the reality, what will be reality after 10 years, I should say, is maybe yes, all those like a type of like a traumatic, like all those injuries would be helped by this. But when it comes to the product, especially the first approved product, it will not like that. It will not work like that, because regardless of its ability of actually solving that problem, many of them would not have a market value. It would not earn money. It would not earn because market is too small or it's too specific or whatnot. So there will be some situation that this product or this technology will do a great job compared to the existing product or technology. And that thing is very large in volume, and people are happy to pay pretty good amount of money to solve the problem. So by combining all those number crunchings, it just become a very attractive market for the product. And then the investors are willing to spend a lot of money to go through all those complicated commercialization process. So after 10, it's like once it is first got approved, I have no idea, because it's something that we are keep learning and discussing with the business people, but it will very likely in reality be one or two indications that satisfy this market condition. But once it go there, but it's been doing so great job there and saves a lot of people in terms of a surgeon's headache and earns more money for the hospitals and saving patients' life. And it's been there for like, say, 5 to 10 more years, then that technology will start to gradually spreading out of that particular indication to out-of-label uses by surgeons, and it becomes cheaper, and FDA become more like giving more trust on the technology, so they are happy to give more indications. So it will gradually increase its usage over time. But initially, it will be very narrow indication where the market value is existing for the first target.
I see. Thank you for that explanation, because I had no idea as to how that was supposed to play out. Let's talk about how the paste actually works. You wrote about some of the components that are in there, and as a Polymer Science podcast, I feel obligated to discuss that, right? So it seems like the main polymer component, just that you might start from, is a polyacrylic acid. And it's modified with an adhesive component, an NHS ester, and as we talked before, that there's a silicon oil sort of media, the stuff that carries it through, and you get this paste. The paste has the oil and these microparticles of polymer.
Yep.
Right. So, to whatever extent you're allowed to discuss, you talked about the NHS being grafted on to the polyacrylic acid.
Yep.
Can you talk about architecturally, right? Normally when I talk about polymers, I tell people who doesn't know what a polymer is to imagine a noodle of spaghetti, right? And that to us is just one linear polymer, but you have, I would imagine, a very complex architecture when you talk about things being grafted onto one another.
Yeah.
So if you were to have us picture what one of these polymers might look like before it becomes cross-linked, can you talk about what that picture looks like?
So, because we are gel guys, like hydrogel guys, we don't talk about a noodle because we always have a cross-linked polymers to form a solid gel. So we always use the analogy of a fishnet. So a fishnet is a polymer network that like just basically soak with the water that form a hydrogel. The hydrogel or this adhesive material is a class of a hydrogel people call tough hydrogel that are mechanically pretty robust compared to the ordinary just the single network hydrogels that people use for like diapers or some like gel electrophoresis kind of very, very brittle and weak gels. So why this gel? Because as we just discussed, the mechanical property of this sealant have to be good. Otherwise, it cannot seal the high pressure or high strength things to the wound. So it's a fishnet, but its fishnet is not a single material fishnet. It actually have a two-component fishnet. So in this particular material, we have, as you mentioned, polyacrylic acid grafted with NH esters as a one fishnet. So if I call it as a polyacrylic acid is like a large fishnet, and NH ester is because it's grafted is kind of a bee's are located in somewhere, some places in that fishnet. But if we use that material alone as a chemical, the problem is that will be biodesic, there will be tissue adhesive, but when they are being equilibrated in a wet condition, it become a hydrogel. That hydrogel will be too weak, will be very weak. It's like it's break like so easily. So you're gonna not have a mechanical property that can withstand a variety of different physiological conditions. So we have another network, fish net, that made out of a chitosan, which is a shrimp or crab-driven polysaccharide, which is biodegradable polysaccharide. So we basically mix these two network or fish net intertwined each other. So this is a very interesting class of material we call a double network hydrogel that are basically intertwined or interpenetrate two different crossing network together. So therefore, they are reinforcing each other to make the resultant multi-network structure of the hydrogel strong. So that's a reinforcement part. But when we talk about chemistry of this sticking thing, there is a reason why we use the polyacrylic acid as a main biodesic network. But not only that, we grafted NH ester. So the polyacrylic acid is one of the simplest synthetic polymer that bears carboxylic acid group. We like the carboxylic acid group for a variety of different reasons. First, it is not too strong acid, so which means it's very abundant in human body as well. But what is interesting about this carboxylic acid group in polyacrylic acid, which is the simplest form of the synthetic polymer that bears a carboxylic acid group, is you have a very impressive ability of forming hydrogen bond with the many different chemical groups that are abundant in biological tissues, including another carboxylic acid group and or primary amine groups. So they are very, very abundant in biological tissues. And this carboxylic acid group and polyacrylic acid can form a hydrogen bond very readily. And we really like this because this is basically the source of immediate or instant stickiness. It's instant stickiness because it form of this is such a physical bond, and physical bond takes a very short time to be formed because it's not a chemical reaction. But the issue is that if we only have this thing alone there, it forms a quite fast stickiness. But the issue is because this is a physical bond with a relatively low bond energy, it is dynamic. It's kind of can be break down over time, and as this carboxylic acid is gradually being neutralized by the surrounding materials in a physiological fluid, it may being shielded by salt ions such as sodium kind of thing. So then it starts to become having less capability of forming hydrogen bonds. So it become unstable over time. So to stabilize this initial stickiness over long term, we have to stabilize this interfacial adhesion by having covalent bond, which is much more robust and stable against over time. So that's exactly what this grafted NH ester doing, because NH ester is one of the most commonly used chemical group for conjugation of proteins in a variety of different things. So those NH ester can interact with the primary amine group, which is one of the most abundant chemical groups in the biological tissues, and undergo a very simple chemical reaction just in aqueous neutral condition and generating very benign byproduct and form amide bond, which is a pretty stable covalent bond. So that having that grafted functional groups on top of an immediately sticky hydrogen bond forming network is helping them to be stabilized over like several minutes of time period. So therefore it would stay there over long-term time period while through which it had to provide a good adhesion to allow this sealing is working.
That's an incredible methodology to do this two-part synergistic effect, right, with the very fast stickiness, and then as those hydrogen bonds start to break down, I guess those some amine groups or amide groups might open up to be able to interact with the NHS ester.
Yeah, so there's one interesting thing that we actually think very clever design is that The NH ester is a great I think the NH ester one of the most loved functional group in biochemistry because it's so good in terms of coupling, forming an amide bond with any amines. But the issue of that thing is it actually unstable if there is water.
Oh, wow. Okay.
It hydrolytically degrades very fast. But why we could still use it? Because our adhesive is starting our adhesive is beginning from dry material. It's like a dry microparticle or dry film. So it doesn't have a water when we prepared it. So in that dry form, this NHS ester functional group can be protected and like shelf preservable. But only when it applied to the wet tissue and absorb water to be sticky, then it start to react with the amine group. And it doesn't matter at that moment because it already formed a covalent bond with the target tissue. So the fact that we take the hydrogel foam at the end of the day, but when we actually prepare and store and before use, it stay as a dry material is really enabled us to take advantage of this nice and simple and benign chemistry without worrying about it being hydrolytically degrading, say, in water, this NHs go away in a few hours and completely degrade away. But we don't need to worry about it because we keep our material as a dry material before use, and then it only become hydrogel only when we actually use it on wet tissue.
Yeah, that's incredible. That was another question you've answered without me having to ask. I was curious as to why, what keeps it without reacting while it's, say, in its packaging or in its tube. And it has to come into a wet environment to get started.
Yeah, so the making everything dry is the way to keep everything unreact each other. But we don't need to worry about being wet because that's the moment that it actually have to react because it's applied to the wet tissue.
Right. Incredible. What are the benefits? A lot of, in this paper, you compared it to some of the already existing FDA-approved materials like the Tacosil. And I noticed in one of the experiments where you were repairing a liver damage in pigs, there was blood accumulation under the Tacosil patch, which of course you didn't have to deal with when you used the paste. The paste filled in all of those crevices. What exactly is not good about the blood accumulation? Why is it best for the paste to be able to get into every space?
So it actually, blood accumulation itself is not exactly the disadvantage. But the issue is really, really at the end of the day, what really matters is bleeding. So bleeding had to stop. So why those material have issues in terms, like say those commercially existing patches have issues in those situations is one reason is we use the pig that with the heparinized. The heparinized means that pig does not have ability of forming blood clots. And this is a very common situation in various surgeries. Say if someone undergoes the cardiovascular surgery, they actually have to be administered either heparin or warfarin to allow their blood not to be clogged. Because think about it, if they are deal with a lot of vascular surgeries, and if the blood clot during the surgery, it will clog some major vessels and the patient will die. So blood thinner have to be applied to keep or deprive of the forming the blood clot. Or some people with the terminal liver diseases cannot form the blood clot well. Or some people lose too much blood, cannot form a blood clot, the so-called coagulopathy. Or someone who have a genetic disease that doesn't have ability of forming blood clot well also cannot clot. But interesting thing is that those patch-like products like the Tacosil from Baxter or all the other existing products, the way they are actually working as a blood-stopping material is they are actually not really sealed because it's very difficult to do it, but instead they are trying to accelerate the blood clot formation of our own body and use that form the blood clot as a sealant.
I see.
So that's good. That's great when the bleeding is tiny, is a kind of very minimal. For example, if we got a paper cut, we got a couple of drops of blood, but when we hold it using tissues for a few minutes, it stops, right? And why it stops is the blood clot formed, and it just seal all those off. But that is very, it becomes ineffective when the bleeding amount is so large. So therefore, the blood clot formation is very difficult to happen in such a large and pressurized situation. And or when the patient is in condition that have difficulties of forming blood clot, then they cannot be used. And that particular liver thing is a condition, two conditions are combined. First, the pig is anticoagulated to simulate the situation the patient have a very reduced ability of forming blood clots. And second, is very deep, so therefore the surface of the liver is actually quite far away from the actual source of bleeding. It's kind of bleeding from the bottom. So to seal that, the whole chunk of the whore have to be form a blood clot to seal off the whole plug. But because the animal or some patient cannot do that, it's very difficult to seal by existing technologies that not really sealed by themselves, but just only promoting the formation of the blood clot to stop the bleeding.
Right.
So that's there. And what we do is, because what we do as a mechanic, we don't care about blood clot. We don't need it and we don't use it. So we just seal something right away by repelling blood and stick on the surface of the bleeding surface directly, regardless of the need of the forming blood clots. So that's why we call it as a coagulation independent. So that's something, that's where the difference is coming. We don't need to wait until blood clot forms, which take at least several minutes. And we don't need to basically differentiate whether animal or patient can or cannot have a good ability of forming blood clot.
Yeah, that's incredible. Really. I realize also we've been speaking for almost an hour and 10 minutes, so I don't want to take up too much of your time. I am more than happy with the discussion we've had so far, but if I were to have any, I guess, last question, what advice you might have for graduate researchers just getting into their graduate career?
Yeah, that's a very tough question, because if I really know the answer, I think I can set up consulting firm, not any company, because that's the question that even many faculty don't know. But if I can make any suggestion, which I actually make every time whenever I have a chance within the group that I have worked, is I think what's really important thing is I know I have been in the field, and the academic field is competitive. That's just the reality. There are so many people. There are so many PhD candidates and PhDs, and people dying for or fighting for whatever, many things, because world is scarce place. There are fierce competition. And I nowadays find that those social medias and all those internet things really make this worse, because people are exposed to the things, and people have plenty of chance to compare themselves with the other peers. And it's just the peer pressure come everywhere, every time, daily and even hourly basis, make people depressed, etc. And I was like that too in my first couple of years, because I could see people do a lot of things, and I just always feel like I have to do better whatsoever. It was unhappy. But what I really want to make advice now is that I think at least when people are keeping the student status, I think we have to just completely forget about it. Just to do something that we think fun, we think meaningful, and we think that we can be convinced ourselves. That is really worthy. Instead of worrying about how many paper we can write for some topic and how good journal we can reach out from that topic or project, just forget about it. But just something that convince ourselves it is important and meaningful. But that process, I believe, is to be very seriously being thought through. Like what exactly the definition of a meaningfulness that we can actually resonate ourselves, not just now, but when we take a look at our life in 10 years after and look back on it, still think that, well, that was a really right choice, that was meaningful thing that I had to do at that moment. And I think asking that questions and try to shield ourselves from internet, the internet that is a worldwide network of peer pressure. I think it's wonderful source of information. We are getting so many information so easily and so quickly. But at the same time, especially early stage graduate students who are start to develop their interest of field and the thesis topic they're gonna work on years afterward. It's really needed some caution that using those internet and social network and all those media based stream of information in more wise way and try to shield off ourselves and forget about something that more like a career researcher would care, such as like how trendy the topic it is, how fancy the topic it is, how the journal would likely be. Like some people publish Nature, some people publish Science on a ludicrous topic just because it looks so good.
Right. Yeah.
But we have to just forget about it, because if someone works in academia for their life, there will be plenty of time they're headaching about those things for sure, just to not to get fired or not tenured. But at least for student status, I think it's important to just forget about it, just learning, just finding out something that resonating or make heart beat a little faster, higher BPM. But it's a very obvious thing that everybody may say, but I just know from my own experience and my experience of mentoring early graduate students in MIT, in this lab, and other places. It's hard. It's very, very hard, because this era of internet, everybody's are interconnected with each other. This period is just hard setup to do that really well. So I think it need an intentional focus of not to do so. Otherwise, we will be exposed. We will get exposed to peer pressure. It makes people unhappy. Yeah. It makes people feeling of unfairness, because it is unfair. It is politics and trendy topics and whatever thing that really affect all those academic publications and whatnot. For example, I can be very frank. If I am not working in MIT, I may work in a very great school, but not as famous or big as MIT. Maybe I cannot publish exactly the same work in this type of a journal that with a lot of publicity. I may have to publish in somewhere else. But that's a reality that we have to headaching off. And nowadays, I'm in the stage that I start to headaching off all those things. But I think we have to forget about it very intentionally and strongly, at least throughout the PhD process, because I really see many of students, even the ones that I train myself, are losing their love of science and engineering just because those realistic pressure that is actually doesn't necessarily to get it to them. It's just automatically flowing to them just because of this internet and all those kind of well-connectedness of. It's a curse. It's a curse of our age. I think it's something that the young grad students, the starting grad students, really have to be careful, because the science and engineering is a rational study. But the problem is the scientists and engineers are human beings. So we are emotional animal. So we have to keep ourselves from unnecessarily being discouraged, stressed out, and etc. Because depressed mind can never be creative.
Yeah, absolutely. This advice resonates very, very much with me. It's very important, like you say, as graduate researchers, to be able to have the heart beating and love what we're doing, to really drive that motivation. So that's I appreciate this advice very, very much. And I have one more question out of my own curiosity. What's next for you? You're a recent PhD graduate. You're listed as just a research scientist. You've got all these projects going for you. So what might be at your front door?
Well, I probably can find a job in university, whatever. I don't know, but I am currently trying to pushing the effort on startup end to commercialize it. And I am willing to spend at least a couple of years out of academic work to see and learn what's the daily thing that I have to deal with when someone really have to do more business side of the things to translate technologies. In my case, it's biomedical device technologies. So that's maybe the next step. And Why I do so? I think it's maybe more relevant for the upcoming generation of grad school. Is it's a sadness that we have to take in our generation, that academia in engineering have been disconnected so much from the real world. It's not anymore very well connected with the real world. We are like, our predecessors have built a garden of their own. So I think already in my generation, we have to give some very strong effort of ourselves to broaden our eyes beyond this tiny world of academia, to learn more about the real world and how things going on. And that's why I'm taking this career plan and steps to hold myself as a full-time academic researcher, but try to do something that I did myself, to see a little other different side of the world. And I believe it will be more and more common and or necessary for upcoming generation of researchers, just because it's probably just how this whole thing would change gradually toward.
Mm-hmm. Mm-hmm. Wonderful. I'm very much looking forward to following your journey as you go along. It's been excellent having you on the podcast today, learning about your work. Thank you so much, Dr. Yuk, for coming onto the show. I can't express how much I appreciate you giving me this time.
Yeah, sure, absolutely. And thank you so much again for your interest and time to chat with me. And I'm not sure whether it's your area, but hope you have a nice evening.
Yeah, hopefully it stays nice here, and same to you. I hope you have a good rest of your evening. Thank you again.
Thank you so much. Yep, bye-bye.
And another big thanks to all of you wonderful listeners for tuning in today and making all that we do worth the while. I sure hope you've all enjoyed this conversation with Dr. Hyunwoo Yuk as much as I did, and that maybe we've all learned a few new things about the wonderful world of polymer science. If you have any questions or feedback regarding this show, or maybe you just feel like saying hello, please reach out to us at polymersciencepodcast@gmail.com. And as always, thank you so much for listening, and we'll see you next time.